Good afternoon and welcome to this talk which will be delivered by James Gopsill. I am Emma Rose, Faculty Projects Manager for the Faculty's Industrial Liaison Office. If you have any questions for our speaker today, there'll be a Q&A at the end of the presentation. Please submit any questions you have in the Q&A tab found at the bottom of your Zoom screen. This talk is part of our Faculty Research Showcase event. The purpose of this week-long event is to demonstrate the breadth of research capability we have in engineering at Bristol, to provide stimulus for a conversation and hopefully future collaboration. I will now hand you over to James, who will talk about designing and manufacturing the future, an introduction to the Design Manufacturing Futures Lab. Thank you.
Thank you, Emma, and welcome all for this afternoon's talk. Just bear with me as I share my screen. There we go. Is that okay? Is that coming up, Emma? Just double check. Cool. I believe it's there for you. So yes, good afternoon, everybody. Yes, welcome to our talk on designing and manufacturing the future. And it's an introduction to the Design and Manufacturing Futures Lab in the School of Civil, Aerospace and Mechanical Engineering. My name is Dr. James Gopsill, and I'm a Senior Research Fellow in the lab. There we go. So today I just want to give you a brief overview of the lab, the research themes that we have in our lab, and then really just give over kind of a quick fire research on a page type aspect, given probably about a minute or two on each of the different key themes that we're currently working on, just to give you a flavour of the research that we do in our lab. And then we'll just finish up on about how we might connect up and follow up on our discussions and potential ideas going forward. And then also open up for a discussion with yourselves. So the lab is, the link's there, dmflab.co.uk. So we've got our own webpage. We are like 15 plus strong group and continually growing. Our key remit for our lab is really developing and pulling through future design and manufacturing capability. So if you see DNM in the slides, that's design and manufacture. We have a wealth of experience. I wouldn't want to know the combined years of experience that we have in the group, but we have a wealth of design and manufacturing experience, starting from the very early concept design stages, all the way through to embodiment and detailed design, and then into prototyping and manufacture and scaling that manufacture to batch and mass manufacturing capability. Whilst we do research and we do focus on different areas, we try to make it application domain agnostic. So yes, you'll see most of our work, we might be linked to the aerospace sector or product design, but we do try and keep our our theory and our design ideas domain agnostic. So we hope to try and apply them across engineering, and we're really keen to work across different sectors. So whilst you might see some domain specific like examples here, we really were open to widening our participation to different sectors and industries of design. So our research area, so the lab itself has got a set of core themes, and we're currently going through, let's say, a pivot in terms of how we market ourselves. But here are the themes that we currently have. We have like novel interactions with computer aided engineering. So how we actually interact with our computer like CAD systems and our CAM systems. So novel ways of doing that. We do a lot in digital twins. Of course, it's kind of the buzzword of the moment. Twinning processes, how we can twin the digital and the physical, and also digital threads, which is that emergent term about how we share data and information across our life cycle. We have novel manufacturing systems. So we're investigating novel ways of how our manufacturing systems interact with one another to produce the products of today and tomorrow. Advanced computer aided engineering. So again, absolutely blue skies, novel ways of modeling our domain and modeling our engineering problems. Next generation prototyping is in the physical domain, and how we actually might enhance our prototyping processes to gain richer information and insights on the rich insights of our prototypes and physical prototyping techniques. Then lastly, we have knowledge management and how we capture and store and manage knowledge throughout the life cycle. So on the right there is our technology readiness levels. So we do broadly, operate across the TRL levels. But like you say, as you'd probably expect, we do primarily focus on probably levels 1 to 5, and then we, engage with industry partners to really bring that, pull that research through to 5, 6, 7, and 8, and to get it out in the industry. So the things I'm showing you there today are the items that we're going to be covering in our 1 minute, research on a page. So at very early stages, we've got quantum computer aided engineering. And 2, we have got the 2 physical or 2 digital. We then will look at digital threads. We will also look at next generation prototyping and different techniques we are developing in that space. We have a project called Pro2 Booth, and that is a physical prototype version control system where we can try and integrate that and twin that with our digital version control systems such as PLM. We have a new project coming on called Brokering Additive Manufacturing, and that's how we might, use how we coordinate additive manufacturing capability across the UK. And then our last one there is artificial intelligence in design and manufacture, how we can apply machine learning and artificial intelligence to support the design and manufacturing process. So the first thing here is quantum computer aided engineering. So we're investigating how quantum can support our engineering practice. So just to give you a little bit of background, University of Bristol is investing heavily in quantum technologies. It's becoming a world leader in quantum technology research, and we've got a number of institutes looking at the fundamental mathematical theory and information theory behind quantum, but also in developing the quantum technologies themselves. So here are all the like you say, the acronyms, QII, QTech, QTIC, are all these centres that are being part of the University of Bristol. So for ourselves, we're really intrigued to see how quantum computing can be used to support our engineering practice. So what we're seeing and observing is our design spaces, as we try to model them, are increasing in size. So we're increasing the number of requirements that we have to meet. And alongside that, our new manufacturing and materials capability is increasing as well. So that's opening up the design space. Additive manufacturing is one such example of that. The problem when we're trying to model these now is that it's leading to parallel scaling of the classical computational resources that we require to model those design spaces. So, typical techniques are mapping, effectively doing a kind of grid. If you see on the figure 1 here, mapping that space out, computing solutions across that space. And we can do design space search where you look for optimum regions. So that's figure 1C there, directing a search to try and find an optimum solution in that space. But nonetheless, no matter which way we route, we have that parallel scaling problem. So we need to start using more and more HPC capacity to actually model our problems. Whereas quantum provides a whole new approach to analyzing these problems. The big opportunity there is actually quantum computing enables us to represent all the options to our design problem in an instant. So when you set up a quantum computer with its algorithms, when it's running in that current state in that moment, it is representing all our options and solutions to that problem. The challenge that we have, and that's what we're investigating, is how we down select in that quantum space, and also how we extract those solutions into our normal world, as it were, the classical realm. So yeah, we need to bring those solutions out of that quantum space. So that's what we're investigating. So we've been doing some work on configuration design. So that's a classic example where you want to look at all the design options that are available to you. Our colleagues in mathematics are looking at heat transfer and how we can do heat transfer problems in quantum computing. Our project partners, NCC and CFMS, are looking at quantum key distribution for encrypted data transfer. Again, a really useful thing for IP when you're trying to share information between supply chain. So we're really keen to be the first to exploit quantum computing in the design context. So that's quantum. The second one is Pro2 Booth, and that's about twinning the physical with the digital. So just a little, did you know, Dyson produced over 5,000 prototypes, and those are physical prototypes, in order to refine the design of the bagless vacuum cleaner. So whilst digital is big talk at the moment, we still do a lot of physical prototyping. And actually Dyson have warehouses full of old prototypes, physical prototypes. And of course, that's a burden to manage and keep and control. So we're saying, how can we twin our physical prototypes and digitize them in effect? So our solution here is called Pro2 Booth, and it's an enabling capability of capturing our physical prototypes and twinning it with our digital counterparts. So those could be the CAD models, the bill of materials. So we're developing at the moment a dashboard, mobile app and platform. As you can see on the right there, we've got some CAD models where we're taking 360-degree photographs of the prototype that will sit within that booth. And what that platform does is enable us to track that information in the prototype. So on the right of there's a network, and that's the kind of information we're capturing. So each of those nodes in that network is going to be a prototype, and we're capturing that rationale of which prototypes link to previous ones. And in those links, we are capturing information through the mobile app about the rationale of why we created that prototype, what insights did we generate. We're also using machine learning to automatically detect the bill of materials and the configuration of that prototype. So what that physical prototype was made of. So that's Pro2 Booth. The next stage is next generation prototyping. So this is novel methods to enhance our prototyping practice. And it's one of the main things that brings us all together as a group. We're really excited still of this mix of physical and digital. One of our key aspects is this idea of tribrid manufacture. So we've been coming up with a series of technologies that bring together additive, subtractive, and fabricative manufacturing principles. So on the right here, you can see some pictures of Lego and then some 3D printed surfaces that attach to that Lego geometry. So to really rapidly iterate prototypes, we use Lego to basically effectively form the infill. So you can quickly create that internal structure, then just 3D print the exterior and then use the interface there to link those bits together. If you want to remanufacture that prototype or an element of that prototype, you only need to edit that bit of surface geometry and not have to reprint the entire product. So it makes it much more rapid than even rapid prototyping is today. In addition, we have replicating mass properties. This has been led by Harry Felton, his PhD, is looking at adding their lead pellets into the additive manufacturing process to reposition the mass properties, so moment of inertia, the center of mass. And we did a couple of studies there of looking at, there we go, out of a drill and identifying where would it be comfortable to have the center of mass for a new drill. And it's really enhancing the prototyping aspect. So early concept designs can actually have the physical properties that you might expect of the final drill or component. So we're getting that rich information much earlier in the design process. We also hear at the bottom right there, so you see some of the design equipment there of the fabricative printers and manufacturing devices putting in components into our prototypes. We're also having 3D printers that are able to print on existing prototypes. Again, not having to then reprint from scratch. We're just appending to existing prototypes to try and speed up that process. We also have next generation prototyping in terms of enabling wider stakeholder engagement. So we're really keen to get more and more people into our concept generation stage. It's shown to really benefit and make sure that we are designing for our suppliers and designing for our customers. But how do they interact in the design process? So here we're coming up with novel methods. Again, we've got some examples here of using Lego for ease for people to interact, deploy their design options, and then have them realized using mixed reality, augmented reality, virtual reality, to actually experience all the different design options and play with those. So we're really getting and engaging that user in the loop with our design process. We've got a few other things of instructor blocks where we put instructions on the actual blocks. So it enables people to understand the requirements as they're building design options. We've got an idea of design by annotation, which is even trying to get away from the CAD system and where you can actually physically annotate the physical model and then have that scanned in, use those annotations to modify on the fly. So we're using all the different types of reality and different interaction methods to get people involved in the design process. Now on to brokering additive manufacturing. So this is about connecting highly distributed and diverse manufacturing capability. So this is a whole new project that we've just recently got funding for. And it's all being driven by the nature of society and how we're moving towards these ideas of big demand. COVID-19 is a perfect case and example of this, where our demands have rapidly changed. You know, we were buying cars, then we're buying PPE. So how does our manufacturing system accommodate for those sweeping changes in product demand? Mass customization is another driver for that, you know, where new fads or new gadgets come on the market and quickly want to be bought and taken up by society. So how do we enable that sweeping change so we can meet those demand profiles? We want to accommodate highly dynamic and distinct constraints. You know, we've seen that, you know, global production has been severed by some of the COVID's restrictions, and some of the manufacturing capability can't change. You know, that's it, the automotive production sector, that is highly optimized to design automotive components and vehicles. So to try and change that to produce something else is a lot more challenging. So we want to try and have some kind of manufacturing capability that can be flexible and produce all manner of components. Another aspect is to facilitate independence. So again, like the aspects of Brexit, the idea that people are keen to have this in-house capability in nations that we can provide for ourselves in times of need and to complement existing practice. So brokering additive manufacturing is the idea of how we could bring the whole of the additive manufacturing capability. So from the hobbyists at home to education with the 3D printers that are deployed in our schools and our universities, it's all the way through to industry and the metal additive manufacturing components and machines that are available there. How do we can bring that together in a global form through some global queuing and agent-based strategies to meet the demand of society? So you see in the little figure in the top right there, and if you go on our little website, we've got a little demo of this idea of these printers and machines acting for themselves, interacting with that queue, that demand of products, and bartering and requesting jobs, and how they coordinate with one another to get the jobs and meet the demand of a nation. The next one, and this is up and coming research, is to physical or to digital. And this is where we're determining where and when to use digital and physical engineering processes in the design process. So again, we've got, you know, again, the big buzz is all about, you know, going over to digital and physical and virtual reality and mixed reality. But also, you know, we know there's a huge wealth of knowledge that can be still contained and is only available through the physical of prototyping, manufacturing, testing in the real world. So at the moment, we're looking to build out a few projects around this. When do we digital and when do we physical? So we're looking at optimizing that design process, configuring it in the manner that we can get the best of both and enable the next generation of products in a much quicker time and time to market. Then we have the digital thread. So digital thread, another aspect, is configuring our digital engineering processes and tool chains. So we've been doing a lot in trying to define what the digital thread is with our partners on the Digital Engineering Technology Institute DETI program. And it's all about how we connect our digital processes and physical processes through IoT and get that information to the right people at the right place at the right time. One aspect that we're really keen and really interested in is the aspect of what digital transformation is leading to, is that we're having an increased amount of digital communication, and the number of models that we're generating to describe the design space. So everything from, you know, CFD models to FEA models to cost models to CAM models to kinematic models. We have now got a greater range and capability of modeling the design space for our advanced components. The challenge is how do we bring those all together, and how and when do we use those models to explore the design space? Because the challenge is now is that, you know, these highly complex models are almost a click away with some of the tools. You know, they're really easy to develop, to deploy, and you can then spin up an instance in the cloud and get those solutions back. But of course, by running all these complex models, it's increasing our carbon footprint of the actual design process itself. So we're looking at, now that we've got a series of models that represent our design space, given that we've got cost models, CAM, CFD, is actually where and when do we deploy them, use them, and what sequence and in what order to ensure that we navigate the design space, come up with an optimum solution in a sustainable way. So we're not, burning huge computational resource to get to an optimum design. We're doing it in an as most efficient way as possible. So a couple of figures on the right here is the idea of that we've got a series of design options that were noted by this over omega and theta, and these are all our parameters that are driving our design. So they could be the lengths, the widths, the heights of our sketches, of our CAD models, the materials that we use in our models, in our products. And then in the middle there, F is our series of functions, all our models, the CFD, the CAM, the cost models. So they're taking, elements, they're taking some of the parameters from our design option, are going to run a function, and then they're going to come out some output to assess its performance. And we're calling that phi there. So it's giving us an assessment of its performance. What we're trying to do is, what order and in what sequence do we run those models to get us to our optimum solution? And that's what figure 2 is trying to articulate there, is in what sequence do we run those series of models in an optimum way. Our last little area is artificial intelligence in design, manufacturing, simulation. And this is where we're actually exploring how we use artificial intelligence to support the design process, less so in about actually, using it in the products themselves. So in artificial intelligence in design and manufacture, it's been led by our colleague, David Jones. We're investigating how we can use AI in the design process. One aspect we're looking at is search and retrieval. So we are using the CAD models of our products. We are rendering images of those CAD models in, the entire sphere of how you might look at one of those components. We can then train a machine learning algorithm on those, and then actually use that. And we've shown really good correlation where you can then take a real world photo of a 3D printed version of the actual component, and then use that ML to then find the index, so use it as an indexer to find the CAD model in your CAD system and retrieve that back to yourself in record time. It really overcomes a lot of the barriers of doing like a manual search for components in a CAD system, where you have to try and describe the geometry that you might be encountering. So it's a really good, easy way to democratize how we search and retrieve for items. And we're seeing really good ideas in terms of in the maintenance sector, where you want to be able to say, hey, look, I've got this component that I need to replace. By taking a quick snap of that photo, you've returned the CAD supply chain model, and you're able then to request that product and that material for your supply chain. We're also looking at how we might use it to capture human perception. So if you see those squares and circles there listed from 0 to 10, it says, when does a square become a circle? Now that has got a mathematical descriptor there, which would define 5 as the the center of the transition point. But if I was looking at that for myself, I might say it's probably more around 8 or 9, where I'd select that square is now a circle. And what we're trying to see there is that actually, where people are perceiving form and geometry, very much in terms of brand, for vehicles is a big one there, for BMWs, Audis, Volkswagen. How do you tell the difference? It's all about the form and how it looks and how it shapes. So what we're trying to do is how can we capture that human perception over the mathematical representation? Because actually there is a difference in how we perceive it to how maybe a computer might compute it. And what we've actually found is that, we can use machine learning to capture that human perception. And what we're doing now is feeding that human perception back into the design loop. So we're actually, like say, if you're designing that next car, whilst you're designing it in the CAD system, you can have that machine learning algorithm in real time give you an update of whether would a human or a human group, a set of participants, feel that represents the brand that you're trying to design for. The other aspect there is also capturing inherent design rules. So at the bottom here, we have a chessboard and a chess set. And what we can do is like say, what are the rules that actually represent a king, a queen, a pawn, or a knight? Again, what we're doing is feeding the machine learning algorithms a series of images of knights, queens, pawns, rooks, and capturing that essence of what it is to be one of those pieces. We can then, as a designer designs in the CAD system, again, using the rendering engine of this CAD system, feed that model back into the ML. So as a CAD, as a user is, designing in that space, they're getting real-time feedback as to whether the machine learning algorithm believes that they are making a king or a queen or a knight. Again, helping them see if they can conform to those rules, whatever those inherent rules are that make it representative of a king or a knight. Equally, we're going that next level up is what makes a piece part of a set. So there are rules to make it a king, but then the rules that say, actually this conforms to a set. So how do a set of pieces look? Again, training an ML on that to then actually capture that. So when people are designing, they can also say that their chess set is part of a set. So really interesting area of getting kind of that human feedback immediately through using machine learning technologies. And there's plenty more, loads more that we do. So it's not just, those are just a few of kind of in a nutshell ideas of what we're exploring. So we are also looking at novel search and retrieval of digital assets. On the top right there, you see a video where we're kind of trying to use the CAD model as our universe. So rather than, typically using the typical Google search, actually using that CAD model as our basis for reality and putting all our information relative to the model. So you can imagine all your reports, all the bill of materials, all the information is linked to that CAD model, and you enter your design world through that model at all times. We do a lot of knowledge and competency and skills mapping using code analysis of reports to identify how terms are used with one another, to see how key themes and skills are developing in an organization. And we've used that to great effect to try and identify what skills are within an organization and how can we define them. And once they're defined, how we can map them to individuals in the company, so we know where the skills lie in the company. That same goes for technology readiness assessments, how we can actually use the reports being generated by, like the likes of the Catapult Center, the likes of universities and academic literature to give an indication of how far technology is along in the TRL levels. We're also looking at aspects of transdisciplinary engineering, and I think I've hinted at that with their kind of novel ways that we're trying to get multiple stakeholders in the design loop and get multiple disciplines in working together more closely to get those insights from different disciplines. And we do a lot of generative design, and at the bottom right there, sorry to replace, we worked with a production company to try and model a spacecraft, the Ether. And actually what came up with this is kind of this hybrid generative design and traditional manufacturing techniques and assemblies to come up with a pseudo-realistic actually approximation of what a spacecraft might look like in the future. What was really nice there is actually we were combining both generative, where generative it should be used, and where more traditional manufacturing processes should be used as well, to get the best of both worlds. You see a lot of generative design being all encompassing, but actually we see it's going to be a hybrid we see as the future there, where we use the right techniques for the right part of your component and product. So I'm sure I've rabbited on too much already, but the main thing I'd like to get away with here today is just show all the aspects of what we do as the lab. We do a lot of things, and we're really keen to connect up. That's something we do. We do lots of collaborations, and we're always keen to collaborate. And I think the big takeaway, I think we like making things, be it digital, physical, or a bit of both. We've done work with design consultants. We've got, again, a wealth of experience in D&M processes and tools. So always welcome to have chats and discussions about, the new tools that are out there, how we might configure stuff, configure tool chains. We do lots of partnering on grants. That's one of our big funding streams. So, EPSRC, Innovate UK, Royal Academy, lots of experience there. Always looking for project partners who are keen to be involved in our research. We have visiting industry fellows. We have PhDs so that we can do case awards and joint collaborative projects with, research internships and secondments, student projects. And, if NDAs, confidentiality IP, or national security classifications, they are all possible. There's no barriers. We've got great, great IP teams and confidentiality agreements and contract teams, so we can always overcome those hurdles. So I don't think, the thing I want to say is there's no hurdles in collaborating. So that's really what I want to say, is, like you say, we're keen to connect up. Hopefully those things might be of interest to you. And happy to hear your thoughts on it. So without further ado, I'll just say thank you for listening. Thank you to all our collaborators and project partners. Not all enough to put on a slide, but here are just some. And again, thank you for listening.
Brilliant. Many thanks, James. It's a really interesting talk and a great overview of the work that you're doing in the lab. A reminder to those that have been watching, please do submit your questions through the Q&A tab at the bottom of your Zoom screen. A couple of questions have come in. The first one from Phil. One design challenge is looking at failure modes. If you have good descriptions and models and AI knowledge, could you generate predictions of life problems?
Indeed. So I say, failure modes is a really interesting aspect to look at. Definitely, yes, definitely. I guess is the answer. Yes, I think that's it. We've got a few, like you say. Actually, it's more like still early stage, but group projects. We're looking at failure modes and effects analysis, and actually looking at historic FMECAs. So even from maybe a subjective element of FMECAs, using historic FMECAs from all our different past products of our collaborators, training ML on those to then, like you say, actually support the process of generating FMECAs going forward. Another aspect in more of the AM space that we've explored, and something that maybe a potential interest is, how we design failure mechanisms in AM parts. So they buckle in a predictive way and maintain that. Again, once we've created those models, you can then run a series of simulations, use that to do a surrogate train of a machine learning algorithm that can give you that information much quicker. So yes, most definitely.
Yeah, thank you. Another question, it's slightly from a different slant. It's more to do with working with individuals. Do you work with individuals with the ideas that you've got, and what criteria would you have for collaborating with people?
Individuals, absolutely. Yeah, I mean, some ways in say individuals, we, of course, like a PhD starts out as their individual and comes into the research group as a team. So it depends what stage you're looking at. So definitely, you're happy to collaborate in that way. We have fellows who are either have been are in companies, but also are maybe have retired or have gone there, are starting up their own business, but want to have some research input. So, we do those kind of industry fellows, so you can visit and have that support. The other aspect I was saying with, if you're an individual, it may be that, I guess you might have a bright idea. You're looking to test out an invention. So we've done in the past, we've worked with inventors who are looking to secure a patent. And have explored that and validated, that it's a feasible, like you say, it's technically feasible. So it helps validate their patent so they can carry it forward. So yes, so we've worked with individuals in a number of ways.
Brilliant. I think in this case, so the person that asked the question, Linda, has said that she's a recent MA design graduate with an invention that she needs help developing. So perhaps you could get in touch at some point.
Absolutely, definitely, yes. That is something that we're happy to do. That's always something that we kind of, like you say, do. That's a little bit of an audit. It helps with the patent attorneys. We've had that where they, we've had that in the past that they've actually, for patent attorneys come to us just for a check for that. Well, sometimes it's a sanity check for them. They go, is this reasonable? Does that make sense? So yeah, absolutely. Also how we convey it in patent language. We're not experts by any means, but yeah, we've done a few in the past. So it's just say how we can convey that information in the patent wording. So anything we definitely help. So I'm rabbiting on that. I'm rambling a bit.
Perhaps Linda, we'll get in touch with you after the talk and get some details. Another question that's come through: what kind of tools do you use to run large multi-physics, multi-parameter optimization models? Is AI such as TensorFlow the way to do these things, or do you have alternative methods other than quantum?
So yeah. So okay, well, I mean, it could be Tool City. I could be here for days for tools. Yeah, so we've got a great collaboration with Autodesk. So they're one of our lighthouse partners at the university. So they give us access to tools that are still, brand new, not even on the market, but also, we use their cloud platform extensively for modeling multi optimizations or objective optimizations, or we do like say multi-physics simulations. So we use their platform mostly, but it's not to say that we don't use lots of others as well. So another one we use is Moose. That's an open source platform as well. So that's really good for multi-physics simulations. So definitely worth checking that out. Might be happy to, again, like I say, we're happy to collaborate and share some ideas on how you might want to use those tools. The other aspect, sorry, there was one other tool. Oh yes, TensorFlow, you were saying? Yes, absolutely. TensorFlow is one of the ones. TensorFlow and Keras, I think Keras Tuner that we use it's either part of the package or it's extension to TensorFlow about how you can configure those machine learning algorithms. Yeah, definitely. Yeah, we use those mainly as well for machine learning, in particular for industry standardization. We do use a couple of machine learning tools that are a bit, let's say, more academic, a bit, I know, a bit strings attached. It's not fully connected up. It's a bit flaky here and there. But when we're working with our industry collaborators, TensorFlow is definitely the way to go. It's well trodden ground, a good package that's widely applied and gives them that standardization. So yeah, we try to use those tools.
Brilliant, thank you. You put a slide up at the end showing some of the industry partners that you've already got. Do you find yourself exploring options of non-engineering industry partners? I can imagine, for example, the brokering additive manufacturing that you talked about could have such a wide variety of people or of industry that might be interested.
Yes, absolutely. Yes. So, to elaborate on that brokering additive manufacturing one, we're working with the School of Management as well. So, in terms of, like you say, academic partners, but that's to get us that engagement with a wider, broader perspective of industry partners. So we've of course naturally pulled in the industry organization, the engineering organizations, but actually what's also quite interesting is to have the business side. So, to actually have the business departments in those organizations because a large aspect of that problem is about the business models. So some of it, say technically it's all achievable. You might say, you can imagine that all the tools are out there. We need to configure them. We need to set it all up. But actually to make it work for a business and for businesses of different scales, from, like you said, the hobbyist in their house to the like you say, the large corporations who maybe have banks of printers in warehouses, how it makes it sustainable for all of them is the real challenge there. So business models is actually one of the big themes, an entire work stream in itself. So again, in short, yes, we're really keen to open up and have wider partners. Like that ether, the generative design model there, that was for a production company for testing for the film industry. So again, anyone who wants to test out some engineering in their domain, absolutely, we're keen to explore those partnerships.
Can you make any comment on environmental sustainability? A lot of your work is obviously based on digital models, digital work. Do you design projects with sustainability in mind?
Indeed, it's really timely. We've just submitted a outline proposal. So fingers crossed, you know, it all goes well, to a sustainable manufacturing call. And that aspect I've talked about there, about the digital thread and how we configure all these models, because it is like you say, like, there are the tools out there. We can create these complex models now that run huge number of computations, so take up a lot of resource. And it is almost a click of a button at some stages where you can go, oh, click another one, I'll change the parameters, I'll click it again. But again, you start using supercomputers all the time, and you run up could be a huge carbon bill. So we have just submitted a outline proposal to say, how do we do that in a sustainable way? How do we be responsible engineers in actually how we design? We're again actually looking on the education side, you know, supporting to our students, you know, with the tools like say Fusion 360 they use for their CAD modeling. They'll happily, because it's in there, the FEA tool, they can happily go in, put the forces on their chain. So like they do a chain sprocket mechanism, say here's the force, calculate that. But actually you can quickly go to them and say, you know, you can do just force times distance and work out the torque. And then just be mindful, but because it's so easy for them just to go, okay, I'll go and run a simulation, but actually you could have just done a hand calculation and get the same result. And that would have been a more sustainable way. So it's a bit of a nuance. It's a bit, you know, it feels a bit of a nuance, you know, to say, oh, which way should I compute the answer? But I think it's going to be a really ever more increasingly important question to answer. Because our electricity bills are just, scaling as our design problems are scaling.
Yeah, absolutely. Great. If there's no other questions from our attendees today, then I won't bring the session to a close. I'd like to thank you all for attending and for your questions, and thank you all to our speaker, James Gopsill. In the current climate, online is the only way we can really do this, and we really appreciate that it's not as interactive as we'd like. However, if what you've heard today or throughout the week has captured your interest, please do get in touch with us. Our Industrial Liaison Office is here to connect you to our academics and students, and contact details will be sent after this event. Many thanks again, and goodbye.
Thank you.